Welcome to CompNovAi, a GenAI-based diesel engine component failure mode predictor by our team Hackathon. This is the agenda. Meet our team. Component Business Unit of Cummins performs inspection of failed engine components covered through warranty for trend analysis and design improvements. However, since this is a manual process and it's costly and time consuming, we are trying to predict the root cause of failure using GenAI technology on historical inspection data. This solution is a proof of concept, and if adopted, it is expected to save nearly $700,000 spent in manual inspection of parts.
We performed exploratory data analysis to select the most correlated features as input for our model training using feature encoding, correlation analysis, and LLP techniques. After the feature selection, we cleaned all the text formatted features to remove junk and duplicate values. This is our data preparation architecture. We created a new column code document by concatenating all the selected features as a dictionary, which was used in creating junking and embeddings.
In order to abide to the Cummins data security policy, synthetic data is being used as an alternative to the corporate data that would only change the technical information of the data while keeping the data structure intact. The RAG pipeline is being used to generate the synthetic data. The same data set is being used for demonstration of this project outside of the Cummins organization. This is our RAG pipeline architecture. This is a sample of synthetic data using Llama 3.1 model. This slide shows RAG pipeline evaluation architecture. We have used the BGE large EN embeddings model and Google's BERT-based uncased model for zero-shot learning to perform ranking of most similar claims on synthetic data. This produced 77% accuracy while validating the synthetic data.
Now we'll be talking about model training and evaluation on real data set. This slide shows embeddings creation architecture. This slide shows various approaches we tried, where approach 1 is zero-shot learning of pre-trained embedding model to provide topmost matching embeddings of a claim and thus providing its label. Second approach, we tried using pre-trained BERT LLM models from Hugging Face and fine-tuned those on our dataset. In third approach, we reduced number of features and concatenated their embeddings by treating those as matrices of 64 by 64 and applied a sequential neural net as well as one versus race classifier model to predict the label. Approach 1 achieved 56% accuracy, whereas approach 2 achieved 9.1% accuracy, and approach 3 achieved 22% accuracy. This makes the zero-shot learning-based model, embeddings model, as the champion model. This slide shows reflection of modeling approaches. Now we'll get into the demo.
We will be using synthetic data for this demo. The user would select claim ID, which then shows them the details of it for viewing purpose. On clicking the send button, they will be able to see the failure mode and confidence score, which is nothing but the probability. Next steps, challenges. Talking about challenges, accessing Delta table outside Databricks environment was a challenge, so we exported it in CSV for UI integration. Improving validation accuracy with fine-tuning was a challenge. We need to focus more on feature selection. Synthetic data yielded higher performance when compared to actual data. SMOT always doesn't help. It caused overfitting. Zero-shot model wins. It did best on our use case. Fine-tuning BERT model is expensive. For 24,000 records, it took 74 hours. We found the accuracy was poor after spending much compute and time. Next steps are build compound AI system by summarizing claim narrative text further, balance our data set better before building models, also set up silent validation methods and utilize user feedback for model retraining. Overall, this POC has been a great learning for us. Thank you, Databricks, for this opportunity.